Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Gravity shapes every moment of your existence. Right now, as you sit or stand, this invisible force pulls you toward Earth's center with an acceleration of 9.8 meters per second squared. It keeps your coffee in your cup, holds the atmosphere around our planet, and maintains the delicate orbital dance of celestial bodies across the cosmos. But what if this fundamental constant suddenly shifted? What if gravity weakened by exactly 10% in a single instant? This isn't merely a thought experiment. It's a journey into understanding how deeply interconnected our universe truly is. When we examine the consequences of such a change, we uncover the intricate relationships between mass, energy, space, and time that govern everything from the smallest atoms to the largest galactic structures. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Imagine the moment when gravity's strength drops from its current value to 8.82 meters per second squared. The change would be subtle at first, so subtle that most people wouldn't immediately notice. You might feel slightly lighter, as if you'd lost about 10% of your body weight instantly. A person weighing 70 kilograms would suddenly experience the gravitational pull equivalent to 63 kilograms, though their actual mass would remain unchanged. The first indicators would appear in precision instruments. Pendulum clocks would begin running slow, their periods increasing as gravity's reduced pull affects their oscillation frequency. Scientists at gravitational wave observatories like LIGO would detect the anomaly within minutes. Their laser interferometers registering unexpected changes in space-time curvature. Seismographs worldwide would show subtle shifts in their baseline readings as Earth's gravitational field weakened. Water would behave differently. Rivers would flow more slowly, their velocity reduced as gravitational acceleration decreases. Waterfalls would appear more graceful, with droplets taking longer to complete their descent. The height that liquids can reach in fountains would increase, while the pressure at the bottom of deep bodies of water would decrease proportionally. Athletic performance would see immediate improvements in certain areas. Jumping heights would increase, though not by the full 10% due to air resistance and biomechanical factors. A basketball player who could previously jump 60 centimeters vertically might now reach 66 centimeters. High jumpers and pole vaulters would break records seemingly overnight, though the euphoria would be short-lived once the broader implications became clear. Aircraft would experience changes in lift and performance characteristics. Pilots would need to adjust throttle settings and control inputs, as planes require slightly less thrust to maintain altitude. However, this seemingly beneficial change would create significant challenges for aviation safety systems, calibrated to current gravitational conditions. The weakening would affect every pendulum-based system on Earth. From grandfather clocks to specialized scientific instruments, timing mechanisms would lose accuracy. A pendulum clock that previously kept perfect time would now run approximately 5% slow, gaining about 72 minutes of error per day. Most remarkably, this change wouldn't be limited to Earth. If gravity weakened universally, every massive object in the universe would experience the same proportional reduction. The Moon's orbit would begin expanding, Earth's orbit around the Sun would gradually increase, and the entire solar system would start a slow but inexorable journey toward a new equilibrium. The universe itself would begin evolving along a fundamentally different path, one where the balance between expansion and gravitational attraction shifts dramatically in favor of cosmic expansion. Earth's response to weakened gravity would be swift and dramatic, beginning with changes that ripple through every layer of our planet's structure. The most immediate and visible effect would occur in Earth's atmosphere, where the reduced gravitational pull would cause significant expansion and redistribution of atmospheric gases. The atmosphere, held close to Earth's surface by gravitational attraction, would begin expanding outward like a slowly inflating balloon. The scale height, the altitude over which atmospheric pressure decreases by a factor of E, approximately 2.7, would increase from its current 8.4 kilometers to approximately 9.3 kilometers. This expansion would cause atmospheric pressure at sea level to decrease by roughly 10%, dropping from the standard 1,013 millibars to about 912 millibars. This pressure reduction would have immediate physiological effects on human populations. People living at sea level would suddenly experience atmospheric conditions similar to those at an altitude of approximately 1,000 meters above current sea level. While not immediately life-threatening for healthy individuals, this change would cause noticeable effects: mild shortness of breath during exertion, slight increases in heart rate, and potential altitude sickness symptoms in sensitive individuals. Earth's oceans would respond dramatically to the gravitational change. The reduced pull would cause sea levels to rise as water expands vertically in response to decreased gravitational pressure. More significantly, the planet's rotation would cause a redistribution of ocean water. Earth's equatorial bulge, currently maintained by the balance between centrifugal force and gravity, would become more pronounced as gravity's hold weakens. The solid Earth itself would begin deforming. Our planet isn't perfectly rigid. It responds to gravitational forces like a very stiff, elastic material. With gravity weakened, Earth would experience what geophysicists call elastic rebound. The planet would literally expand slightly, increasing its radius by approximately 2 to 3 centimeters. This expansion would trigger seismic activity as crustal stresses readjust to the new gravitational regime. Tidal forces would weaken, proportionally, affecting both oceanic and solid Earth tides. The twice-daily rise and fall of ocean levels would decrease by 10%, altering coastal ecosystems that have evolved around current tidal ranges. The solid Earth tides, the barely perceptible twice-daily flexing of the ground beneath our feet, would similarly diminish, affecting precision scientific measurements and GPS satellite accuracy. Earth's magnetic field would experience subtle changes. The planet's magnetic field is generated by convective motion in the liquid outer core, driven partly by gravitational forces. Reduced gravity would alter these convection patterns, potentially causing variations in magnetic field strength and orientation. While not immediately catastrophic, these changes could affect satellite operations, radio communications, and navigation, systems that rely on magnetic field measurements. The planet's internal structure would begin a slow readjustment. The immense pressure at Earth's core, created by the gravitational weight of overlying layers, would decrease by 10%. This pressure reduction would affect the behavior of materials under extreme conditions, potentially altering the boundary between Earth's solid inner core and liquid outer core. Mountain ranges would experience reduced gravitational stress, potentially leading to subtle changes in their stability profiles. While mountains wouldn't suddenly grow taller, the reduced gravitational load would affect slope stability and erosion patterns. Some areas prone to landslides might see increased activity as the delicate balance between gravitational pull and structural strength shifts. Atmospheric circulation patterns would begin changing as the reduced pressure gradient affects wind patterns. The jet streams, those high-altitude rivers of air that influence weather patterns across continents, would weaken and potentially shift position. This would mark the beginning of significant climate changes that would unfold over the following months and years. Underground water systems would respond to the pressure changes. Artesian wells might see increased flow rates as the reduced gravitational pressure allows groundwater to rise more easily. Conversely, systems dependent on gravitational flow would see reduced rates, affecting everything from municipal water supplies to natural spring flows. The weakening of gravity would fundamentally alter the orbital mechanics that have governed our solar system for 4.6 billion years. Every celestial body, from the smallest asteroid to the largest planet, would begin adjusting to a new gravitational reality that threatens the stability of the cosmic dance we call home. The Moon would be among the first casualties of this change. Currently orbiting Earth at an average distance of 384,400 kilometers, our natural satellite maintains its stable orbit through a precise balance between its orbital velocity and Earth's gravitational pull. With gravity reduced by 10%, this balance would be broken immediately. The Moon's orbital velocity of approximately 1.02 kilometers per second would now be too fast for the weakened gravitational field to maintain its current. Orbital radius. Following Kepler's laws of planetary motion, the Moon would begin spiraling outward, increasing its orbital distance to maintain equilibrium with the reduced gravitational force. The new stable orbital distance would be approximately 427,000 kilometers, an increase of over 42,000 kilometers. This orbital expansion would have immediate consequences for Earth. The Moon's gravitational influence on our planet would weaken with the square of the distance, causing tidal forces to diminish beyond the direct 10% reduction from gravity's weakening. Ocean tides would become significantly smaller, and the Moon would appear noticeably smaller in our sky, reducing the frequency and duration of total solar eclipses. Earth's orbit around the Sun would face similar disruption. Our planet maintains its nearly circular orbit at 150 million kilometers through a balance between orbital velocity and solar gravitational attraction. With the Sun's gravitational pull reduced by 10%, Earth would begin moving to a new orbital distance of approximately 158 million kilometers. This orbital expansion would increase Earth's orbital period from 365.25 days to approximately 386 days, extending our year by nearly 3 weeks. More critically, the increased distance from the Sun would reduce the solar energy reaching Earth by approximately 5%, initiating significant climate changes that would compound the atmospheric effects already underway. The other planets would experience proportional orbital changes, but with varying consequences based on their individual characteristics. Mars would move from its current orbital distance of 228 million kilometers to approximately 241 million kilometers. Jupiter, with its extensive system of moons, would see its orbital family expand, proportionally, potentially destabilizing some of the smaller, more distant satellites. The asteroid belt would become gravitationally unstable. Many asteroids currently maintained in stable orbits by the gravitational influence of Jupiter and Mars would find their orbital configurations disrupted. Some would spiral toward the inner solar system, while others would be ejected entirely. This redistribution would increase the risk of asteroid impacts on the inner planets, including Earth. Saturn's magnificent ring system would expand outward as the planet's reduced gravity weakens its hold on the countless ice and rock particles that form the rings. The rings would become less dense and more diffuse, gradually losing their sharp definition as particles migrate to higher orbits or escape entirely. The solar system's stability depends on countless gravitational resonances, mathematical relationships between orbital periods that keep celestial bodies in stable configurations. The Kirkwood gaps in the asteroid belt, regions kept clear by Jupiter's gravitational influence, would shift and change. The Trojan asteroids that share Jupiter's orbit would lose their stable positions at the Lagrange points, those special locations where gravitational forces balance perfectly. Comets from the outer solar system would be affected differently depending on their current position. Those in the distant Oort cloud, already barely bound to the solar system, might escape entirely as the Sun's weakened gravity releases its tenuous hold. Conversely, comets currently approaching the inner solar system would follow different trajectories, potentially missing their predicted closest approaches to the Sun or taking longer to complete their orbits. The delicate gravitational relationships that have kept our solar system stable for billions of years would be irreversibly altered. While the immediate changes might seem manageable, they would set in motion a cascade of effects that would reshape the architecture of our cosmic neighborhood over the coming millennia. The atmospheric expansion caused by weakened gravity would trigger one of the most significant consequences of this scenario: accelerated atmospheric escape. Earth's ability to retain its atmosphere depends on a delicate balance between the kinetic energy of gas molecules and the gravitational energy required to escape to space. With gravity reduced by 10%, this balance would shift dramatically in favor of atmospheric loss. At the exosphere, the outermost layer of Earth's atmosphere extending from about 700 kilometers to 10,000 kilometers altitude, gas molecules with sufficient velocity can escape Earth's gravitational pull entirely. This process, known as Jean's escape, normally occurs at a very slow rate. However, with reduced gravity, the escape velocity would decrease from 11.2 kilometers per second to approximately 10.6 kilometers per second. This seemingly small change would have profound implications. Lighter atmospheric gases, primarily hydrogen and helium, would begin escaping at rates hundreds of times higher than current levels. More concerning, even heavier gases like oxygen and nitrogen would experience increased escape rates, though at initially manageable levels. The expanded atmosphere would create a larger target for solar wind, the stream of charged particles flowing from the sun at speeds of several hundred kilometers per second. The solar wind normally deflects around Earth's magnetosphere, but the enlarged atmospheric envelope would extend beyond this protective magnetic shield. Direct interaction between solar wind and atmospheric particles would strip away gases through a process called atmospheric sputtering. Water vapor in the upper atmosphere would become particularly vulnerable. Solar ultraviolet radiation would dissociate water molecules into hydrogen and oxygen, with the lighter hydrogen escaping rapidly to space. This process would gradually dry out Earth's atmosphere, reducing the greenhouse effect that helps maintain surface temperatures. The climate implications would unfold across multiple timescales. The immediate 10% reduction in atmospheric pressure would alter weather patterns by changing the relationship between temperature, pressure, and humidity. Storm systems would behave differently, with reduced atmospheric density affecting everything from hurricane formation to the intensity of thunderstorms. The expansion of Earth's orbit, moving our planet approximately 8 million kilometers farther from the Sun, would reduce incoming solar radiation by about 5%. This decrease, combined with the gradually thinning atmosphere, would initiate a cooling trend that could push Earth toward an ice age within decades. The reduced atmospheric pressure would lower the boiling point of water from 100 degrees Celsius to approximately 96 degrees Celsius at sea level. This change would affect everything from cooking and industrial processes to the behavior of natural hot springs and geothermal features. More significantly, it would alter the water cycle, changing evaporation and precipitation patterns globally. Cloud formation would be affected by the altered atmospheric conditions. With reduced pressure, water would vaporize more easily, but the expanded atmosphere would distribute this moisture over a larger volume. The net effect would likely be changes in cloud cover patterns, affecting Earth's albedo, the amount of solar radiation reflected back to space. The jet streams, those high-altitude wind currents that drive weather patterns across continents, would weaken and potentially shift position as pressure gradients change. This would disrupt established weather patterns, potentially causing droughts in some regions while bringing unusual precipitation to others. Plant and animal life would face multiple stresses simultaneously. The reduced atmospheric pressure would be equivalent to living at higher altitude, affecting respiration for both plants and animals. Photosynthesis would be impacted as the partial pressure of carbon dioxide decreases, potentially reducing plant growth rates and crop yields. Aquatic ecosystems would experience changes as atmospheric pressure affects the solubility of gases in water. Reduced pressure would cause dissolved gases to come out of solution more readily, potentially creating oxygen-depleted zones in bodies of water. This would be particularly problematic for marine life already stressed by other changing conditions. The ozone layer, which protects life from harmful ultraviolet radiation, would be affected by the changing atmospheric dynamics. While the total amount of ozone might not change immediately, its distribution would alter as atmospheric circulation patterns shift. Some regions might experience reduced ozone protection, increasing ultraviolet exposure and its associated biological risks. Over longer timescales, measured in centuries to millennia, the continued atmospheric loss would fundamentally transform Earth's climate system. The planet could potentially lose enough atmosphere to create conditions similar to those on Mars, with a thin atmosphere unable to support liquid water at the surface. Life on Earth has evolved over 3.8 billion years under the constant influence of our planet's current gravitational field. Every biological process, from the circulation of blood in mammals to the transport of nutrients in plants, has been shaped by gravity's steady 9.8 meters per second squared pull. A 10% reduction would create unprecedented challenges for virtually every living organism. Human physiology would face immediate stresses. The cardiovascular system, evolved to pump blood against gravity's full force, would initially benefit from the reduced gravitational load. However, this apparent advantage would quickly become problematic. The human body maintains blood pressure and circulation through complex feedback mechanisms calibrated to current gravitational conditions. Reduced gravity would trigger these systems inappropriately, potentially causing blood pressure fluctuations, dizziness, and circulatory problems. The musculoskeletal system would begin rapid adaptation within days. Bones, which maintain their density through gravitational stress, would start losing calcium as the mechanical load decreases. This process, similar to what astronauts experience in zero gravity, but occurring at a planetary scale, would weaken bone structure across all age groups. Muscle mass would similarly decline as the constant work against gravity decreases, leading to widespread weakness and mobility issues. Plants would face particularly severe challenges. Their entire architecture depends on gravitational orientation. Through a process called gravitropism, roots grow downward following gravity's pull, while shoots grow upward against it. With gravity weakened, these fundamental growth patterns would be disrupted. Root systems might grow more horizontally, reducing their ability to anchor plants and access deep water sources. Stems and trunks would experience less gravitational stress, potentially leading to taller but weaker growth that couldn't support the plant's weight. The transport of water and nutrients in plants relies heavily on gravitational pressure gradients. In tall trees, gravity helps drive the movement of sap and water from roots to leaves through the xylem system. Reduced gravity would impair this transport, potentially limiting the height that trees could effectively maintain. Giant sequoias and other tall species would face particular stress as their existing height becomes unsustainable. Under the new gravitational regime, aquatic ecosystems would experience disruption as water density and pressure relationships change. Fish and other aquatic organisms use swim bladders, gas-filled organs that control buoyancy, to maintain their position in the water column. These systems are precisely calibrated to current atmospheric and water pressure conditions. The reduced atmospheric pressure would cause swim bladders to expand, forcing fish to constantly adjust or face buoyancy problems that could prove fatal. Marine food chains would collapse from the bottom up. Phytoplankton, the microscopic plants that form the base of ocean food webs, would struggle with altered water density and reduced pressure. Their ability to maintain optimal depth for photosynthesis would be compromised, potentially triggering a cascade of effects through the entire marine ecosystem. Flying organisms would initially seem to benefit from reduced gravity, requiring less energy to maintain altitude. However, the simultaneously expanding atmosphere would create thinner air at all altitudes, reducing lift and making flight more difficult. Birds would need to fly faster or work harder to generate the same lift, while insects would face even greater challenges due to their smaller size and different flight mechanics. Pollination systems would face disruption as both plants and their pollinators adapt to changing conditions. Bees and other flying insects would need to adjust their flight patterns and energy expenditure, while plants might alter their flowering timing or structure in response to gravitational changes. This could lead to temporal or physical mismatches between plants and their pollinators, threatening reproduction in both groups. Soil ecosystems would experience fundamental changes. The reduced gravitational compaction would alter soil density and structure, affecting water retention, nutrient cycling, and the habitat of countless microorganisms. Earthworms and other soil-dwelling creatures would need to adjust their movement patterns and feeding behaviors as the physical properties of their environment change. Predator-prey relationships would shift as different species adapt at different rates to the changing conditions. Some species might gain advantages in mobility or resource access, while others would face new disadvantages. These changing competitive balances could lead to unexpected species extinctions or population explosions that further destabilize ecosystems. The Reproductive cycles of many species would be affected. Animals that use gravitational cues for migration, mating, or other seasonal behaviors would face disruption as these environmental signals change. Birds that migrate using gravitational sensing might lose their navigational accuracy, while animals that time reproduction based on environmental pressure changes could face reproductive failures. Over longer timescales, the ongoing atmospheric loss and climate changes would create increasingly hostile conditions for life. Species unable to adapt quickly enough would face extinction, while those with greater adaptive flexibility might survive to inhabit a fundamentally transformed Earth. The rich biodiversity that characterizes our current planet would likely give way to a much simpler ecosystem dominated by the most resilient organisms. Human civilization's technological infrastructure represents thousands of years of engineering development, all calibrated to Earth's current gravitational constant. From the precision timing systems that synchronize global communications to the water distribution networks that supply our cities, virtually every technological system would require fundamental recalibration or complete redesign to function in a 10% reduced gravity environment. GPS satellites, which provide positioning accuracy to within meters by measuring precise time differences between satellite signals, would immediately begin losing accuracy. These satellites maintain their orbits through careful balance between orbital velocity and gravitational attraction. The reduced gravity would cause orbital decay as satellites move to new stable positions, disrupting the carefully maintained constellation geometry essential for accurate positioning. Navigation systems worldwide would begin showing increasing errors within hours, affecting everything from smartphone maps to aircraft navigation and precision agriculture. Power generation systems would face widespread disruption. Hydroelectric facilities, which rely on gravitational potential energy to drive turbines, would experience approximately 10% reduction in power output as water falls with less force. Dam operators would need to increase water flow rates to maintain power generation, potentially straining water resources and flood control systems. The reduced atmospheric pressure would also affect the efficiency of steam turbines in thermal power plants, requiring operational adjustments across the electrical grid. Transportation infrastructure would require immediate adaptation. Elevators, designed to counteract current gravitational loads, would initially provide excessive upward force, potentially causing dangerous acceleration and stopping problems. Automatic braking systems in vehicles would be calibrated for current deceleration rates and might not provide adequate stopping power as the relationship between weight and friction changes. Aircraft would face complex operational challenges. While reduced gravity would decrease the weight-related component of fuel consumption, the simultaneously expanding atmosphere would reduce air density at all altitudes. Pilots would need to fly at higher speeds to generate equivalent lift, potentially negating fuel savings. Airport operations would be disrupted as landing and takeoff distances change, requiring recalculation of runway requirements and safety margins. Water distribution systems would malfunction as reduced gravity affects pressure gradients in pipes and pumping systems. Municipal water towers, designed to provide water pressure through gravitational head, would deliver reduced pressure to consumers. Pumping stations would need recalibration to maintain water pressure in high-rise buildings and elevated areas. Sewage systems relying on gravitational flow would experience reduced flow rates, potentially causing backups and sanitation problems. Manufacturing processes would require extensive adjustment. Assembly lines using gravitational feeding systems would need modification as parts move differently down inclined surfaces. Precision instruments calibrated to current gravitational conditions, from laboratory balances to industrial scales, would show systematic errors requiring recalibration or replacement. Communication systems would face disruption beyond GPS failures. The expanded atmosphere would affect radio wave propagation, altering the performance of everything from cellular networks to satellite communications. Ground-based antenna systems might require repositioning as atmospheric refraction changes, while satellite communication links would experience signal degradation as orbital positions shift. Chemical and pharmaceutical industries would encounter unexpected challenges. Many industrial processes rely on gravitational separation of materials with different densities. Reduced gravity would slow these separation processes, affecting product quality and production rates. Laboratory procedures using centrifugation would require adjustment as the effective gravity changes, potentially affecting research and quality control processes. Construction and architecture would face long-term challenges. Existing buildings and structures designed for current gravitational loads would experience reduced stress, but also altered dynamic responses to wind and seismic forces. The reduced atmospheric pressure would affect building ventilation systems and potentially cause problems with sealed building envelopes designed for current pressure differentials. Nuclear facilities would require careful monitoring as reduced. Gravity affects coolant circulation systems that rely partly on natural convection. While not immediately dangerous, these changes could require operational modifications to maintain safety margins in reactor cooling systems. Financial systems dependent on precise timing would experience disruption as atomic clocks and other precision timing sources require recalibration for the new gravitational environment. High-frequency trading systems that rely on microsecond timing accuracy could face significant operational challenges, potentially affecting global financial markets. The Internet infrastructure would face cascade failures as GPS timing synchronization fails, affecting everything from data center operations to the precise timing required for high-speed financial transactions. The backbone of modern digital civilization would require extensive modification to maintain functionality. Medical equipment would need recalibration or replacement. Devices that measure fluid pressures, from blood pressure monitors to intravenous flow controllers, would show systematic errors. Surgical procedures relying on gravitational drainage or precise fluid management would require adjustment, potentially affecting patient care during the critical transition period. The immediate chaos of weakened gravity would be merely the opening act of a cosmic drama that would unfold over millions of years, fundamentally altering Earth's destiny and our solar system's evolution. Understanding these long-term consequences requires us to consider how gravitational changes ripple through time, affecting everything from planetary atmospheres to the ultimate fate of life itself. Over the first 1,000 years, Earth's atmosphere would continue its gradual escape to space. The initial 10% reduction in gravitational pull would compound over time as atmospheric loss accelerates. Computer models suggest that Earth could lose 20 to 30% of its atmosphere within the first millennium, transforming our planet's climate into something resembling early Mars. The Moon's continued outward spiral would have profound implications for Earth's stability. Currently, the Moon acts as a gravitational anchor, stabilizing Earth's axial tilt at approximately 23.5 degrees. This stability provides the seasonal regularity that has allowed complex life to evolve. As the Moon recedes to its new equilibrium distance, its stabilizing influence would weaken proportionally to the square of the distance. Without strong lunar stabilization, Earth's rotational axis would begin to wobble chaotically over timescales of millions of years. This axial instability would create extreme climate variations as different regions experience wildly varying amounts of solar radiation. The polar ice caps would alternately melt and refreeze, causing dramatic sea level fluctuations that would make long-term habitability extremely challenging. The solar system's architecture would undergo fundamental reorganization over hundreds of thousands of years. As planetary orbits expand and stabilize at new distances, gravitational resonances that have maintained asteroid and comet populations in stable configurations would be broken. The asteroid belt would become more diffuse, with many objects either falling toward the inner solar system or being ejected entirely. This orbital reorganization would significantly increase the bombardment rate of the inner planets. Earth, Mars, Venus, and Mercury would face elevated asteroid and comet impact frequencies for millions of years as the solar system seeks new gravitational equilibrium. These impacts would further stress any remaining ecosystems and could potentially deliver the final blow to complex life on Earth. The reduced solar energy input from Earth's expanded orbit would trigger irreversible climate changes. The 5% reduction in solar radiation, combined with atmospheric loss, would push Earth toward permanent glaciation. Over timescales of 10,000 to 100,000 years, ice sheets would advance from both poles, eventually covering most of the planet's surface in a global ice age far more severe than any in Earth's history. Ocean chemistry would undergo dramatic changes as atmospheric pressure continues to decline. The reduced pressure would cause dissolved gases to outgas from seawater, creating oxygen-depleted oceanic conditions. Marine ecosystems, already stressed by climate change, would face additional challenges as the fundamental chemistry of their environment shifts. The weakened gravity would affect Earth's internal dynamics over geological timescales. Reduced gravitational pressure in the planet's interior would alter the behavior of materials under extreme conditions. The boundary between Earth's solid inner core and liquid outer core might shift, potentially affecting the magnetic field generation process. A weaker or more unstable magnetic field would provide less protection from solar radiation, accelerating atmospheric loss and making the surface even more hostile to life. Continental drift would slow as reduced gravitational forces affect the convective processes that drive plate tectonics. Volcanic activity might decrease as the pressure-driven processes that create magma chambers operate under different conditions. This geological slowdown would reduce the planet's ability to recycle carbon and maintain atmospheric composition through volcanic outgassing. The implications extend beyond Earth to our understanding of planetary habitability throughout the universe. This scenario demonstrates how finely tuned the conditions for complex life really are. A mere 10% change in one fundamental constant cascades through every aspect of planetary evolution, ultimately rendering a life-bearing world uninhabitable. For other potentially habitable exoplanets discovered by missions like the Transiting Exoplanet Survey satellite, this analysis highlights the critical importance of gravitational stability over geological timescales. Planets in systems with unstable gravitational environments, perhaps due to nearby massive companions or evolving stellar masses, would face similar challenges to our hypothetical Earth. The ultimate lesson of this cosmic thought experiment is profound. The universe we observe today represents an extraordinarily unlikely combination of physical constants and initial conditions. Our Earth exists in a narrow zone of gravitational stability that has persisted for 4.6 billion years, allowing the gradual evolution of complex chemistry into the rich tapestry of life we observe today. In this imagined future, human civilization would face an existential choice: adapt to an increasingly hostile Earth, or venture beyond our transformed planet to seek new homes among the stars. The same weakened gravity that doomed our world might, paradoxically, make it easier to escape Earth's gravitational well, offering a final ironic gift as our species contemplates its cosmic future. The story of gravity's weakening serves as a reminder that the cosmos operates on scales both vast and delicate, where the slightest changes can transform entire worlds and the very possibility of existence itself.